So okay, so let's go to the actual content, and we start with some basic points, recalling basically some basic points that you well partly remember from high school, which is factoring expressions, and what we need for this is the so-called quadratic identities. These you actually saw in your high school courses. So what were they? Just to remind you, if you see some expression like a plus b squared, the first one over here, if you work around these, if you get rid of those brackets, then you will see it's this is actually equal to a squared plus 2ab plus b squared. Same for a minus b squared. If you get rid of those brackets, a squared minus 2ab plus b squared. And the final one, a plus b times a minus b, that's a squared minus b squared. So while this is all right, so what we are going to need is basically knowing these expressions, these quadratic identities, the other way around most often. If you see some expression like the right hand side, like a squared plus 2ab plus b squared in the first line, but you need to recognize, oh, actually this right hand side is actually the same. You can rewrite this as a square, a plus b squared. So what you need to do, if you forgot them, you need to learn these quadratic identities by heart, and in particular from the right hand side, from the sum to the left hand side to the product. Well, why is that? We're going to need those to actually do factoring. What is factoring? Factoring basically is writing a sum of terms, right hand sides in these expressions, as a product of factors, which is the left hand side in these three examples. So let's see that once again. So what's factoring? Factoring in algebraic expression means write it as a product of factors rather than as a sum of terms. So in this example, we have x squared plus x. Well, that's not a product, it's a sum, right? It's x squared plus something else, namely x squared plus x. So those are the two terms. The right hand side, which is evidently the same, you see there's a product. It's x times something. It's x times x plus 1. So this x and the x plus 1 are the two factors going into this product. So here it's sort of pretty obvious that this is the case, but so we are actually going to look at sort of perhaps some slightly less obvious cases in these exercises. So let me actually look at these three expressions, these three factoring exercises on paper. So let me go to the paper here. So the first of these expressions that we have, the first exercise is this one, y squared plus 6y plus 9. Can we rewrite this as a product of factors? Well, remember the quadratic identities, in particular remember a plus b squared equals a squared plus 2ab plus b squared, and now observe that the forms of these two expressions are rather similar, in particular if we see that actually 6 is just 2 times 3, 9 is 3 squared, so if we identify the b with a 3 and the a with a y, then actually these expressions look remarkably the same. Y squared plus 2 times 3 is 6 times y plus 3 squared, right? So the y would equal the a, the b would equal the 3, and then we exactly recognize this expression. So now we can use this quadratic identity. We can rewrite this sum of terms into the product over here as follows. This should equal y plus 3 squared. So what have we done? We started with a sum of terms, 1, 2, 3 different terms. We rewrote it as a product of two factors, namely y plus 3 times y plus 3, or in other words, y plus 3 squared. that's the first example. So let me also do the, well, let me skip the second example. You can see it on the slides. So let me go directly to the third exercise. And this third exercise takes this form. X squared y squared minus 25 z squared. Now, how does this resemble one, or bring it to recollection, one of these quadratic identities? Well, perhaps you observe that x squared y squared is a square, right? It's x y squared. 25z squared is also a square, namely it is minus 5z squared. This is the same. What do we have here? The difference of two squares. So now the alarm bell should ring, and you should recognize actually a plus b times a minus b, this third quadratic expression, is just the difference of the squares of a and b. We have here a difference of squares. You can now rewrite it, going from that side to that side, as a product of, well, the a plus b and the a minus b. So what's a? Well, the a is, in our case, the xy, first square, xy, plus the b here is 5z, so plus 5z, and I need to multiply this by a minus b, which will then be xy minus 5z. So again, by using this third special quadratic identity, I've rewritten sum, or rather the difference in this case, of two terms, x squared y squared minus 25z squared, as a product of two expressions, namely the first one xy plus 5z times the second one xy minus 5z. Okay, so let me briefly go back to the slides then. So this first one is done here actually on the slide, so it gives the same outcome as we had on paper, fortunately. The second one I skipped, but if you go ahead and have a look at that, you'll find that this will also be using this second particular quadratic identity, namely the one involving the minus, well, the total working out this particular example is done on the slide, and actually in two different but related ways. So have a look at that at home. The third one was this difference of two squares, x squared y squared minus 25z squared, and again that's what we just did on paper. Okay? So why do we want to do this? Why would we like to sort of rewrite a sum of stuff into a product of different factors? Well, the main reason that we need to do this is because this allows us to actually say stuff about whether something equals 0 or whether it's positive or negative. So how is that? So it's here, let's consider some numbers a, b, and c. And suppose that we know, well, for instance, if you look at the first line here, suppose that we know that a is a positive number, so it's bigger than 0. B is a positive number, it's bigger than 0. And C is a negative number, smaller than 0. Do we know something about the sign of a plus b plus c? Well, not really, right? So if c is really much bigger negative than a plus b, then of course this a plus b plus c will become a negative. While if c is relatively small, then perhaps this will remain positive and might even get 0. So this information doesn't tell much about this sum of terms. Does it tell us something about the product of a, b, and c? Yeah, sure. You multiply a positive number by a positive number and multiply that by a negative number, well, the outcome is always going to be a negative number. Same thing for some other example. In some cases, actually, you can say something about what the sum is of these three numbers, in particular if they have the same sign. So if all are negative, well, okay, then the sum of these three numbers is also going to be negative. But in all cases, we actually can say something about the product. And the special one, and also especially important one, is if we know that one of these factors, in this case b, is actually 0, well, that does not tell us anything about what a plus b plus c is, but definitely we know that in this case the product of a, b, and c is going to be 0. And that's information that's going to be immensely useful, in particular if you're going to solve equations and inequalities. See that a bit later. Okay, before we do that, there's just one more thing that we need to do, is that is have a look at factoring of actual fractions. What was a fraction again? Well, something like a half, a third, easy fractions. So we learned how to add up fractions in grade school, and basically the same way that we used to do this, that we can do this for these simple numeric fractions. We would also like to be able to do this for fractions that have sort of more symbolic nature. So let's have a look again on paper how this works. So just to remind you, to set the scene here, how would we do the simple fractions example, a half minus a third plus a sixth. How do you add up fractions? Well, you cannot just go ahead and add up stuff. You first have to worry that in this case the denominators are different at this point, and we need to make these denominators the same. Now how do you do that? Well, you recognize that 6 of course is 2 times 3. So if you want to make all these different fractions into fractions that have the same denominators, what can we do? Well, let's just multiply the first fraction, both its numerator and its denominator, by 3. We then get this 3 times 1 divided by 6, that's 3 times 2. The second fraction, we need to multiply both the numerator and the denominator by 2, so 2 times 1 gives us a 2 in the numerator, 2 times 3 again gives us the 6 in the denominator. The third one's already in the correct form, because we just have this plus 1/6. And now we're in business, because we see that now we have 3 fractions which have the same denominators. So that means we can actually add up the different numerators. So we arrive at, well, 3 minus 2 plus 1. Let's do 6. Well, this is the answer, except that we can of course simplify it a bit by dividing now the numerator and the denominator by this common 2, this equal to 1. So this is of course what we know. So we're going to use this same technique basically to also simplify fractions of this form that we have on the slide. We just copy it here for you. X minus y divided by x plus y minus x divided by x minus y plus 3xy divided by x squared minus y squared. So again, we have 3 different fractions. And we want to add them up, but we can't because the denominators are the same. So what should we do? We should try to make those 3 denominators to be the same. So is that difficult? No, well, not so much, because if you look at particularly this third one, x squared minus y squared, you might sort of again get triggered and see this this third special quadratic identity. You see that it actually takes the form of x plus y. If we just substitute a bx plus y times x minus y. It's a difference of 2 squares. X squared minus y squared is x plus y times x minus y. And now it should ring some alarm bell again. So what can we do to make these 3 things the same? Well, we should try to rewrite them in stuff which has as denominator the same x plus y times x minus y. So how do we do that? Well, for the first fraction, perhaps now it looks obvious to you that we need to multiply the denominator by x minus y, because that's the bit that we're missing here. X plus y times x minus y. It also means that we need to multiply the numerator, the x minus y that we already have here. We also need to multiply that by that same x minus y, so we get the x minus y squared. Right? So we multiplied both the denominator and the numerator of this first fraction by x minus y. Same thing for the second fraction. Here we have to multiply by x plus y. So what do we get? Minus x times, I need to multiply the numerator by x plus y, and I also need to multiply the denominator by x plus y. And the x minus y is what you already had over here, so you multiply it again, both numerator and denominator by x plus y. And these first two fractions already have the same denominators now. So what about the third one? As we just covered, this one is actually of the correct form by use of this special quadratic identity. So we just leave it as it is in terms of the numerator, and we just use this quadratic expression to see, well, actually this x squared minus y squared over here is equal to x plus y times x minus y. And now we're in business, because now we see we have three fractions which have the same denominators. That means we can actually add up the numerators. So let's do that. At the same time, actually already sort of get rid of the brackets. So what do we have here? The first one, if we get rid of the brackets, x squared minus 2xy plus y squared. That's from getting rid of this first numerator brackets here. Second numerator gives us minus x times x. That's minus x squared. Minus x, be careful here, this is minus x times y. Minus x times y. This minus actually, read it as a minus 1 if you wish, multiplies this x, and thereby also in this bracket the xy part. And then finally we have the plus 3xy from the final fraction. That's the numerator, just adding up the three numerators. Because the denominators were all the same, we can just keep that denominator over here. X plus y divided by, times x minus y. So are we done? Well, almost. We can actually simplify again this numerator a bit, because, look what happens. There's an x squared over here, there's a minus x squared over there, so those two cancel. That's going to be convenient. So what about the xy terms? Well, there's minus 2xy over here. Minus xy gives me minus 3xy. If I add to that plus 3xy, those terms cancel as well. These two actually together cancel against that one. And the only thing that remains there is this y squared. Y squared divided by this denominator, x plus y times x minus y. So again, what happened? We started with a sum of three fractions. They had different denominators. We made those denominators equal by multiplying the numerator and the denominator of each of these fractions with a suitable expression. So in that case, we had three fractions with the same denominator. We could add those up. Now we arrive at an expression which is actually not anymore a sum of terms or different of fractions, but it's actually a product. It's y times y divided by x plus y times x minus y. So again, we have factorized this sum of fractions. Okay, so let me go back to the slides. There we are, hopefully. So the same exercise is also done on the slides. You can have a look at that as well if you want. So it should be the same. Fortunately, the final outcome looks the same, so that hopefully gives some confidence in the correctness of this result. So this is how we simplified some fractions. So we look into factorizing. The next thing is, what can we do with factorizing? Well, that's solving equalities and solving inequalities. So that's going to be the next bit.